Okay, and the principal subject of my talk is the phenomenon of positivity in very different mathematical subjects, in different mathematical areas. So my principal aim of this talk is to try to find some generalizing ideas why the positivity property is so important in such different topics. Okay. Here I presented some keywords related to my talk. So we see the Sturm criterion, the geometry of totally positive Grassmannians, logarithmic concavity property, stable polynomials, hyperbolic polynomials, and two famous polynomial graph invariants. And this talk is based on some joint results with students from Yaroslavl, Denis Golitsyn, Alina Kutuzova, my colleagues Boris Bychkov, Anton Kazakov, Eduard Lerner, and Sofia Mukhamedzhanova. I will start by recalling the principal definitions of totally positive matrices and the appearance in problems of root localization of real polynomials. So just from the beginning, real matrix A is called totally positive. It's if all its minors are positive, and it's called totally non-negative if all its minors are non-negative. The very known Binet-Cauchy theorem states the following rule for calculating the minors of the product of matrices, and this fact provides the following property. The set of totally positive and non-negative matrices is closed under multiplication. It is due to the Binet-Cauchy theorem. Another very important theorem, I'd like to say the structure theorem of positive matrices is the generalization of the Perron-Frobenius theorem. I'd like to recall the basic facts. The Perron-Frobenius theorem: let M be a real matrix with positive elements, the positive minors one by one. Then it has very strong properties. So the eigenvalue with maximal absolute value is real and positive. And moreover, this eigenvalue is a simple root of the characteristic polynomial, and the corresponding eigenvector can be chosen such that all its coordinates are positive numbers, which play sometimes the role of probabilities. Definition due to the very famous book of Gantmacher and Crane. A definition of the oscillatory matrix. So a matrix M is called oscillatory if M is totally non-negative and there is some natural number k such that M power k is totally positive. And there is a structure theorem of Gantmacher and Crane about oscillatory matrices. So a matrix M is an oscillatory n by n matrix. Then it has simple real positive spectrum. Here the lambda it are the eigenvalues of this matrix. And Vk is an eigenvector corresponding to the eigenvalue lambda k. So it's a part of this theorem of Gantmacher and Crane that the eigenvector with number k has, it has k minus 1 sign alternatings. Okay. And initially, this class of matrices was introduced in the context of some physical problem of small elastic oscillations. Another subject, but in fact, strongly related to the total positivity properties. Let us consider just a sequence of numbers, of real numbers, AI, of non-negative real numbers, and this sequence is called log concave if we have such an inequality, and log convex if we have the inequality in the inverse order. Okay, with such a sequence, one could associate a matrix, a Toeplitz matrix, which is constructed by this formula. And one can state the question of such sequences, those Toeplitz matrices are totally positive. This property is stronger than log concavity, but log concavity is a consequence of Toeplitz positivity. Another type of matrices associated with number sequences is a so-called Hankel matrix, which is a symmetric matrix constructed by this formula. And there is a family. There is a family of sequences such that those Hankel matrices are totally positive. So this property is also stronger than the log convexity, but it implies this. This interpretation of log concavity, for example, in terms of some positivity property of some matrices, is very useful from the point of view of this theorem. If A of z and B of z are log concave polynomials, it means that the coefficients of these polynomials are log concave number sequences. And there are no zero coefficients in the middle of the sequences, then so is the product of these polynomials. It is not evident from the definition, but if we go to the side of Toeplitz matrices, it is quite simple that the product of polynomials correspond to the product of matrices, and Cauchy-Binet formula implies the what is called two-total positivity. It means that it is a property of being positive all minors 2 by 2 of the matrix. But the Cauchy-Binet formula is valid for just for partial minors, for minors 2 by 2 of the product of this matrix. So this passage to Toeplitz matrices is very useful by this algebraic tool.
Dima,
yes.
What happens at the end in that definition of your polynomials with you get to the highest coefficient? What do you then do for what do you set an plus 1 if it's a degree n polynomial?
So I don't quite understand your question. Here it is an infinite matrix.
Yeah, but your polynomial is finite. So what do you take when you're beyond the degree of the polynomial? What do you take an to be?
Zero. They just zeros.
Just zero. Okay, thank you.
Yes. Okay.
And you say this no internal zero. You mean no? So all coefficients are non-zero, and then all just larger coefficients here, bigger coefficients are zero. Okay.
Absolutely. Okay. There is a very interesting theorem. So different mathematicians have to part in demonstration of this theorem. So I have mentioned just some of them. It states the following. If we have a finite sequence of numbers, and it is Toeplitz total positive, if and only if the polynomial has all zeros, so all its zeros are real negative numbers. So what is called now the hyperbolic stable polynomial. And there is a infinite version of the statement, which is presented here. So one-sided infinite sequence of numbers is Toeplitz total positive if and only if this series is expressed as some exponential factor multiplied by ratio of series of product, sorry, and all zeros are negative, and on all poles are positive. Okay. Some words about hyperbolic polynomial.
Sorry. It was written that sum of all BIs is negative, or each BI is negative.
No.
So all alphas and betas
of alpha
are positive.
Yes.
I don't understand. Betas all positive, but their sums is negative.
I think it's a mistake.
So there are no condition on the sum of all alphas and betas.
No. Just that. No. Just that they are alphas and betas are positive.
Okay.
I don't remember now the condition of regularity of. So is it a formal series or it's a convergent series? But for me, it's important the finite version. Just I mentioned this just to say that there is an infinite analog of this equation, of this theorem. Just a few words about hyperbolic polynomials. Definition: a polynomial p of z of degree n is called hyperbolic real polynomial with real coefficients if it has n real roots. And it is more natural to work with the notion of hyperbolic polynomials of multiple variables. And the definition is the following: a homogeneous polynomial p of x now it is a vector from the m-dimensional space. This polynomial, homogeneous polynomial of degree n, is called alpha hyperbolic for alpha a vector from the same space if p of alpha is not equal to 0, and the polynomial of one variable. So it is a value of a polynomial grand p big P in the direction alpha, has n real roots for all values of x, where x is a vector from m-dimensional space. It could be difficult to understand this definition if you see it for the first time. Just an example, very simple example. Let X be a real symmetric matrix. So it's an element of the linear space of symmetric matrices, symmetric real matrices. Then we can see the polynomial P of X, a polynomial on this vector space, which is just the determinant of the matrix X. And this polynomial is hyperbolic in the direction alpha, which is just the unity matrix. Is it evident for you?
Yes.
Okay, so it's a statement that the real symmetric matrix has a real spectrum.
Yeah.
Okay, but it is exactly the property that this polynomial on the linear space of symmetric matrices is hyperbolic. Okay. There is a very interesting and I suppose not very known technique of guarding cones related with the notion of alpha hyperbolic polynomials. It is the following object. Let P of X is an alpha hyperbolic polynomial. So it's hyperbolic in the direction alpha. The hyperbolicity cone Cp alpha is the connected component of alpha in a set of vectors beta from the same space, from the same m-dimensional real space, such that P of X is hyperbolic in direction beta. So alpha is a component of this, is an element of this connected component, but we can see the deformation of vector alpha, which gives us also a hyperbolic direction for the polynomial P. To my opinion, non-trivial and very interesting statement is the following result. It is contained in different papers of Garding. So the first statement is that this hyperbolicity cone of the polynomial consists of such vectors beta that the polynomial P alpha T plus beta has only negative roots. So there are many very evident examples of such statement. For example, just the real cone in R3 has the interior part of this cone. Just one part of this cone is the guarding cone of this function, and it is evidently characterized by the positive by the coefficients of the same sign in coordinates of these vectors. It is evidently related with the asymptotic directions of surfaces of the second order and its generalization. So just some statement about hyperbolicity cones. The first one, that this cone is characterized, now it is characterized by some stability condition, because the roots of this auxiliary polynomial are only negative, and this is a convex object. So okay, Just a remark that this
Sorry.
construction. Yes.
Sorry, and what is the convex cone in case of symmetric matrices? You gave an example of that.
I suppose that it is a symmetric matrix, positively definite symmetric matrix.
Okay, thanks.
Evidently. Okay. And just a remark, I'm not specialist, but I'm very interested in this direction, this construction, this concept of guardian cones is a
I don't hear anything, or maybe it's my problem.
Yeah, you turned off your yeah. Dima, you turned off your microphone.
Is it better?
Yeah.
Now we can hear you.
I'm sorry.
Yes.
Electricity is always a problem. So such a construction has application to the theory of nonlinear differential equations. So the concept of this guardian cone is applied to the space of solutions of some differential equations. And so just a remark, which is interesting for me. Okay. Another appearance of this phenomenon of stability, stable polynomials in some recent results in integrable systems is the following stuff. So let X be a point of the Grassmannian of K subspaces in n-dimensional space. We associate with such an object just a matrix K by n, and calculate the kth minors of this matrix. So big I here is just the subset of indices of, for example, of columns, and this subset is contains k columns. We construct a homogeneous polynomial of this kind. And so xi is also I here is a multi-index. So we take the product of variables corresponding to the columns of the matrix M and consider such polynomial.
So what is the dimension of vector x small?
X small is a scalar, but it's a product. It's xi1 multiplied by xi2 xik.
So little x is a k-dimensional vector and I is multi-index.
Yes, and here it is a product of coordinates. So it's xi1 multiplied by xi2, etc.
I thought Dima meant that x with a lower index I capital, so x I1, etc. x ik.
Xi is x xi1 xik. So it's a homogeneous multi-linear.
It's a polynomial of in n. So x is a vector is in n-dimensional space.
Yes.
And here you have, no, now I understand. That is a monomials made from this one.
It's a homogeneous of order k polynomial on the space of dimension n. And the statement is the following. It's a theorem of Purphu of 28. The polynomial constructed by this form is stable, but in a little bit different sense. So it has no zeros in the upper half plane in each direction of our space of vectors x. So it is just multiplied by the complex unity to make relation with the previous definition. So in this definition, the polynomial is stable if and only if the matrix M is totally non-negative. The matrix M from which we constructed these Blücher coordinates. And this construction is applied. This construction is applied in some recent papers. For example, in the paper of Abend and Glinevich for constructing a real regular solution for the KP hierarchy. Okay. Now I will talk about some different matter about properties of polynomial invariants, polynomial graph invariants. Some definitions. Let G be a graph and X the set of colors. For convenience, I will take in mind just the just n colors, the elements of this ring. The chromatic polynomial key G of n is the number of coloring of vertices of the graph G by elements of X, such that the neighboring vertices are colored by different colors. Its very close analog is the flow polynomial, and it is defined as follows. We call a flow on a graph G a function on oriented edges, this function on edges of G with values in X, such that at each vertex there is a condition of zero circulation of this flow. This function also this function is ampere, and here Eij is the edge oriented from I to J. The flow polynomial Fgn on the graph G is a number of non-zero, nowhere zero flows.
Is it related to Kirchhoff relations on the network? No.
Yes, sure. But it's some story. But this condition is just the Kirchhoff relation. So the flow polynomial is just a number of nowhere zero flows on gamma with values from 0 to n minus. If G is a planar graph and G star is its dual graph, then the flow polynomial and the chromatic polynomial are related by this formula. So just some dual object, but sometimes it's better to work with one of them, sometimes with another. there is some generalization of flow polynomial, which is called complete flow polynomial. Let G be a graph, and we choose some subset of external vertices of this graph. Ij, as before, is an oriented H going from if vertex to the G vertex. A flow with values in K in some field with boundary condition P Vx to K is a function f on edges with the same property. At each internal vertex, we impose the Kirchhoff rule, and in external vertices, we allow some sources. The complete flow polynomial is the following partition function. So here we consider the sum over flows with boundary conditions, and we in each definition we suppose some choice of an even function I of the flow on an edge, and this function possibly depends on an edge. Okay, I'd like to show you that the partial choice of the function I.
Is there any condition of this PI? Is it should be sum of 0 or something like that?
No.
No conditions on PI?
Here, PI. I don't see PI. PI. No. It's just whatever you want. There is no condition on PI.
So I can put all equal to 1, for instance. Yeah?
You can put all PI to 0, and it will be the same as the flow polynomial without external terms, without boundary conditions. Okay. A particular choice of the function I is given by this formula. So it's 0 if the flow on this edge is 0, and is 1 if the flow is non-zero. If we apply this choice in this general definition, we obtain just the standard flow polynomial, which accounts the know where 0 flows on the graph. There is another choice of the function on edges, which is given by this formula. So here is the value of the flow. It is we take the square of this value. We divide it by some h weight, which have the meaning of the conductancy in electrical networks, and the complete flow polynomial imitates the power of the flow and some partition function. So the sum of energies of flows in electrical network, and the relation with the real electrical networks is that distribution of the flow distribution for an electrical network is the extreme of this functional. Okay, but it's a different, long and very interesting story. Another subject, another aspect of the total positivity. The important part of the recent work of Junha is the log concavity of very different objects. of polynomial invariants of graph, matroids, and morphisms of matroids. For example, it demonstrates the following theorem, that the coefficients are E of the chromatic polynomial of a graph, of every graph, is log concave. In particular, this result implies the conjecture of unimodality of this sequence, which was stated by Ronald Reed in this year. And Junha produced some very powerful generalization of this result to the category of matroids. I'd like just to recall one of the definition of matroid in terms of the rank function. So we have some set X and the ensemble of subsets of the set X, and the rank function is a function on subsets satisfying such conditions. So its value on the empty set is 0. It has some property of this type related with the triangle inequality, and this inequality, inequality important in the definition of the matroid. With each matroid, one relates a characteristic function. So here is the definition of this characteristic function. So it depends on one parameter lambda, and which is calculated by as a sum over subset of our set X. The lambda is taken in the power of the rank function of this subset. So
what was S in that formula?
S, I'm sorry, S.
Maybe just A?
Maybe just the number of elements of A. Yes, it is possible. Yes. Boris, do you remember?
I think A, but
A.
yeah.
Okay, I'm sorry, it's A.
I'm not sure.
For example, if G is a graph, when one relate with this graph, graphic matroid M, those underlying set is a set of edges, the basis spanning trees, the independent sets correspond to forests, and the rank function is just the number of edges minus the number of connected components. In this identification, the characteristic function of the matroid is just the chromatic polynomial of G. But the statement of Junha with his co-authors is that the characteristic polynomial of every matroid is log concave. So this property has very deep mathematical nature. And the proof of this statement is of very geometrical nature. So, for example, the proof of representable matroids, it means that they are represented by some matrices in some vector spaces or in some modules over fields. In arbitrary characteristic is based on the De Concini-Procesi compactification model. Okay. Another few results about logarithmic concavity. of a version of the flowing chromatic polynomial. It is called relative flowing chromatic polynomial. The definition is given here. So a relative chromatic polynomial of a graph G with some chosen subset of external vertices is also the number of coloring of vertices of this graph. The colors in external vertices are fixed, and the colors of adjacent vertices are different. The result of my colleague Edward Lerner, just a recent result, if G is a chordal graph, and I will explain what is the subset of chordal graphs, and Vx is just a complete graph, a click in a graph G, then the relative chromatic polynomial is log concave, and the chordal graph is something like triangulated graph. The formal definition is that each cycle of length 4 has an arc separated this cycle. Okay. And the next part of my talk is devoted to the appearance of the notion of total positivity in the problem of localization of zeros of a polynomial, of a real polynomial. I'd like to recall you familiar Sturm criterion. Let f be a real polynomial. One construct the Sturm chain. It is defined by the Euclid algorithm with a starting point, which is just the derivative of the polynomial f, and then we apply the Euclid algorithm with just a choice of minus sign minus here, and we get a chain of polynomials, and then we define a number Vf depending on x, which is just the number of sign alternations in the Sturm chain in this sequence of functions at the point x, and we omit 0 values, just omit. Then the Sturm theorem says the following: let f be a real polynomial, then for each interval AB, the number of simple roots of f in the interval is equal to the difference of values of this function v at points A and B. We consider the Sturm matrix associated with the Sturm sequence. So di here are just the factors in the Euclid algorithm, and here di are on the diagonal. We consider now the case of the maximal of the Sturm sequence, Sturm chain of maximal length. In this case, all factors here are just linear polynomials, and in this case, we can represent Sturm matrix as the linear function on X with just the constant matrices G and H. a theorem proved with students of Yaroslavl State University state the following: let f be a polynomial of this type with maximal Sturm chain. The maximality here means that it is of the length m+1. In such a case, all roots of the polynomial f are real and negative. That is, the polynomial f is stable hyperbolic if and only if I'm sorry, hyperbolic if it is in the case a equal 0. So in this case, this condition is equivalent to the oscillatory property of the matrix, of this matrix, which is constructed from the Jacobian, which is constructed by a Sturm matrix. In particular, for a equals 0, we get an equivalence of two conditions: that the polynomial is a stable hyperbolic, and the matrix G-1 H is oscillatory. Okay, I have some minutes to provide to your attention some geometric interpretation of this result. So in totally positive geometry, there is one of the basic problems to get positive parameterization of positive geometrical object. For example, the positive Grassmannian, just the Grassmannian here is a set of k-dimensional subspaces. Okay, as before, we associate to such matrix the Plücker coordinates, which are just minors of this matrix. Okay, and the totally positive Grassmannian is a subset of the Grassmannian, which consists of subspaces. Those all Plücker coordinates are of the same sign, so they can be chosen positive, for example. In the case of the Grassmannian of two planes in n-dimensional space, one has Plücker coordinates parameterized by two indices I and j, and one has Plücker relation which are quadrics and which are represented by these formulas. One of the problems in positive Grassmannian is to find minimal exhaustive subset of minors such that their positivity implies the positivity of others. And there is a theorem in the particular case of the Grassmannian 2n. It is given, yes, it is presented here. So the set of exhaustive positive coordinates on the Grassmannian 2n is given by the triangulation of the n-gon. And in these triangulations, we correspond to each edge of a triangulation a minor on the Grassmannian. So the statement is like this, and I'd like to make a relation with a different problem. So let us consider the group of lower triangular unipotent n by n matrices. In this group, we can consider the subset of Toeplitz matrices of this type. So they are related, obviously, with the problems of characterization of stable hyperbolic polynomials, as at the beginning of my talk. One can introduce the following coordinates on this space. These are the lower left-hand corner minors of this Toeplitz matrix. There is a theorem of Constance-Ridge, which says, which states that the set of totally non-negative matrices in this cell of Toeplitz matrices admits an effective parameterization by this set of minors. So precisely this theorem says that this map is a homeomorphism of these positive varieties. And the statement involves very interesting geometry. For example, the quantum cohomology ring of partial flat varieties. Our statement is of very close nature, so we parameterize some also some positive cell. Let us call the set of matrices G-1H appeared in the theorem appeared in our theorem. So our statement on negativity of roots can be expressed in terms of just of the oscillatory properties of the matrix H and the property that G has positive elements. And these conditions also can be expressed as the positivity of some minors on of our matrices. So it is a question, friend, in fact. So we parameterize the same object as the positive cell of Ridge, and we have such embedding of our positive cell to the positive cell of Ridge, and it is interesting task of totally positive geometry to compare the positive parameterization. Okay, thank you very much.
Thank you.
Thanks, Dima.
Yeah, thanks.
Спасибо.
Okay, I could not state other questions to myself.
Okay.
But my talk was principally the family of questions.
Yeah. Can you give any probably hint as to how the proof is obtained of your theorem? We have about 5 minutes left.
It's just the application of the Gantt-Macher-Crane theorem.
I see. I see.
Because you see the Sturm sequence. It is an object of Gantt-Macher-Crane linear algebra. The calculation of alternatings is the principal tool in his in the approach.
Okay. Okay. Thanks.